Sir, we have already introduced you to all the participants in the last session, and right now in this platform there are more than 170 participants have joined. Uh, uh, so today Professor Swagatam Das sir from ISI Kolkata will tell about the dynamic and constant optimization problems. Sir, I request you to share your slide and start.
Let me try to share. Can you check whether my slides are visible or not?
Yes, sir. It is visible, sir.
Uh, can you check if it is visible on, full screen mode is also visible?
No, sir. It is not coming on full screen mode.
Can you see the change of the slide?
No, sir. No change in slide, sir.
Okay, just hold on.
Sir, if you share the entire screen, then it will work, sir.
Yeah, just a moment. So I hope you can see the full
Yes,
screen now,
yes,
right?
sir. Now it is perfect, sir.
Okay. Good evening, everyone. So I'm going
Sir,
to.
can you just please change the slide if it is?
Can you see the slide changing?
Yes, sir. Yes, sir. It is now perfect, sir. Slide is also
Sure.
there. Sir.
So, good evening, everyone. I'm going to share some of my own research experiences with the non-convex and real parameter constraint optimization problems with evolutionary computing. As we all know, optimization problems are everywhere, from engineering design and finance to artificial intelligence and healthcare. However, in the real world, optimization rarely happens in an unconstrained setting, where there is no limitation or bound on the optimization variables, right? And we often face limitations in resources, strict regulatory requirements, or physical constraints that make the problem significantly more challenging. And there is where constrained evolutionary optimization comes into play. Unlike the traditional optimization techniques, evolutionary algorithms provide a powerful, nature inspired approach to navigating complex, nonlinear, and multimodal landscapes, all while handling constraints efficiently. So, today, in next 40-45 minutes or so, I will take you through the principles, challenges, and some recent emergent techniques in the field, exploring how modern evolutionary techniques are redefining the problem solving under constraints. So as I said, optimization is the numerical process of determining the decision variables which could minimize or maximize an objective function while satisfying one or more linear and or nonlinear constraints. Constraints are certain equations or certain inequalities that impose additional restriction on the decision variables in the decision space. In a plethora of real world applications, we see the emergence of non convex objective function and non-convex constraint functions with multiple local optima and with a very small feasible region. So in general, a COP, which is a short form for constrained optimization problem, can be defined as you can see over the screen. We are minimizing f of x being this decision variable vector with n such search variables or the objective function. And GIX is the ith inequality constraint, which you could always write as GIX less than equal to 0. HIX or HJX here is the jth equality constraint. And as you see, uh, G and H are respectively the number of inequality and equality constraints. And apart from that, the LBK and UBK are the lower and upper bounds respectively for the ith or the kth here decision variable. So this is generally the constraint optimization problems. And in general, the constraints modify the search space. For example, if there are constraints, two types of solutions are defined for a COP. One is a feasible solution that satisfies all the constraints of the problem, equality and inequality both. And the other type of solutions are called infeasible solutions, which disobeys at least one of the constraints involved. Infeasible solutions cannot be considered as final solutions, and the primary objective of constraint optimization technique is to find a globally feasible optimal solution, that is, an optimal solution that satisfies all the constraints. And that means these blue dots in this picture, which are kind of dragged into this corresponding orange dots in this bluish region. This bluish region is the feasible region. Every point in this region satisfies all the constraints. And if we have, infeasible solutions, which we must make some sort of repairing or some sort of processing of these infeasible solutions so that they can become feasible later on. Okay, and so this is a connected feasible region. The feasible region is not like islands in an ocean, and all the regions are connected. But it could so happen that the problem, based on the complexity of the problem, the feasible regions can also be disconnected. Okay. And the actual feasible minimum or the global feasible optimum is this blue star. These red solutions are infeasible, the green solutions are feasible in the right diagram. Okay. So, and this is basically an example of disjoint feasible regions. There are many ways to deal with feasible solutions, and a simple way would be to ignore the infeasible solutions from participating in the formation of a new solution. As you all know by now, in evolutionary computing, we have an existing set of solutions and we apply genetic variation operators on these solutions like crossover, mutation, etc. to give rise to a new set of solutions. And we may completely ignore the infeasible solutions to take part in creating the new solutions. It can be done simply by replacing the infeasible solutions with feasible solutions from the population. However, the shortcoming of this method is that it does not exploit the search space properly, as some of the infeasible solutions may be very close to the feasible optimum, okay, or the global optimum, and contain important information about the globally optimal basin or landscape. And this approach also fails. This approach means this ignoring all the infeasible solutions. This approach also fails to locate a globally optimum solution of the problem, which has multiple feasible regions, as you can see in the right diagram. And these multiple feasible regions are disconnected, separated from each other by parts of the infeasible region. Let us take an example of a real world problem. In fact, several such problems from the real world have been compiled in our paper, which you can see at the bottom, a test suite of non-convex constraint optimization problems from the real world and some baseline results, published in the Swarm and Evolutionary Computation Journal in 2020. And one such problem is this heat exchanger network design. It is a part of the chemical processing system, and it determines to a large extent the energy efficiency of a chemical process. The heat exchanger network integrates the hot and cold process streams in a process in order to reduce the amount of heating and cooling utilities. And it is a non-convex, non-linearly constrained problem, a set of hot streams that must be cooled and a set of cold streams that must be heated are given. And the flow rates have fixed heat capacity and inlet and outlet temperatures are specified for these streams. Then the problem amounts to getting automatically a heat exchanger network configuration that minimizes the investment of cost of the heat exchangers while satisfying the criteria of minimum utility cost, minimum number of heat exchanger units. So this problem has a very clear physical meaning to the chemical engineers who work in such process plants. It is a problem which has several local minima, and it looks like this. This is the mathematical description of the problem. So you have this sort of a complicated objective function, x1 by 120 x4 whole to the power 0.6 and so on. You have all these equality constraints, 9 equality constraints, and you also have bound constraints on each of the variables. And the bounds are quite heavily disparate in their range. So you can see that x4, x5, x6, they vary between 0 and 0.005 something, 0.05 something. And there are other variables which vary in the scale of 10 power 4, right? So scale of the variables is a very typical problem here. So in our paper, we compiled a test suite of 57 problems. If you go through this paper, and it is heavily used if you want to publish anything in this area, usually the reviewers recommend that you select a few real-world problems from this test suite and test your algorithms on that. And these problems are very difficult to solve because of the complex nature of the objective and constraint functions, the substantial number of nonlinear constraints, and the low volume of the feasible region. Usually the feasible regions are very small. Okay? And this is the first time we compiled standard real-life problems benchmarking new algorithms in an efficient and unbiased manner. These problems are supposed to capture a wide range of difficulties and challenges that arise from the real-life optimization scenarios. We put this problem in the competition and special session for real-world single-objective constraint optimization at the CEC 2020, the Congress on Evolutionary Computation 2020, and also the GECO 2020. GECO and CEC are the two biggest conferences in the realm of evolutionary computing, as we know. And we can classify the problems into 6 groups based on the real-world application. 7 such problems are dedicated to industrial chemical process, 7 such problems to process synthesis and design, 19 problems from mechanical engineering, and so on. And the number of design variables or decision variables range from 2 to 158. Inequality constants can be as high as 148 in number. And the number of equality constants can range up to 148, and inequality constants can vary from 0 to 91. Now, coming to this competition, as you can see in the bottom line, the competition was inviting algorithms to be run on this set of 57 problems, and when we ranked them as per the results and so on, we found that the winner algorithm is this self-adaptive spherical search algorithm. And spherical search was a recently proposed population-based meta-heuristic for solving such continuous non-convex optimization problems. It has a few very interesting characteristics. You can try your hand on it. This is not inspired by some directly inspired by some phenomena of nature like tons and tons of other algorithms. It is an algorithm which mixes both the principles of evolution and also mathematical programming. That's why we call it spherical search. Not the name is not taken from some animal species or something. And this paper won the Editor's Choice Award in Applied Soft Computing Journal. It was published in 2019 at first. It uses less number of parameters to tune, betterly balances the exploration and exploitation during the search. It is rotationally invariant, so if the search space coordinates rotate, the variables, the spread of the candidate solutions are not affected. It maintains high diversity during the search. And it also, like differential evolution, it also has the contour matching property. So the solution points, the candidate solution points, try to closely orient themselves along the contours of the search space. The self-adaptive parameter tuning procedure was proposed on top of the regular spherical search, and a popular epsilon constraint selection scheme, which was specific for solving the constraint optimization problem, along with a gradient-based repair method, were integrated within the framework of the algorithm to efficiently handle the constraints. Then this algorithm was incorporated in this competition, 2020 Gecko competition, as a self-adaptive spherical search algorithm for real-world constraint optimization problem. This is the first paper in the bottom. If you look at the ranks and other algorithms in this competition, you can see the SASS self-adaptive spherical search was the winner. Then we have Shed, which is a real-world single objective constraint optimization problem solver with SHED. SHED stands for Success History Based Adaptive Differential Evolution, a very efficient state-of-the-art variant of DE. Then we had in the third position SCMA GES, which is a modified covariance matrix adaptation evolution strategy for real-world constraint optimization problems, and so on. So these are classical families of algorithms, and their variants specifically designed to handle such real-world constraint problems. So the first 8 ranks are being shown in this slide. Now, constraint handling techniques. There are various constraint handling techniques. Several types of COPs have been observed in diverse research areas where multiple additional conditions can restrict the feasibility of the solution space. So, evolutionary and swarm-based meta-heuristics have been widely applied to bound constraint problems due to their population-based approach and ease of implementations. These algorithms were primarily designed for bound constraint problems. Bound constraint means only the variables are bounded. But using different CHTs, which is a short form for constraint handling techniques, their applications can be extended to handle more complicated COPs. Okay? And several such CHTs have been proposed in practice, of which 6 major ones are listed in this particular slide, of which obviously the oldest and most well-known are the penalty methods. Penalty function-based techniques, in fact, you can see the Lagrange's multiplier-based method as a penalty function approach. The penalty function approaches are arguably the most widely used ones to handle constraints. They increase the fitness value of the infeasible solution by using a penalty factor to a certain level. Consequently, such solutions are less likely to participate in reproduction or survive to the next iteration. Finer adjustment of the penalty factor for various degrees of constraint violation is considered as the main limitation of these techniques, because you need to do such adjustments very carefully. Researchers proposed different adaptive approaches for fine-tuning the penalty factor also. In fact, if you use penalty function approach, then the COP can be converted into an unconstrained optimization problem. Also, you can use, if you look at approach number 5, which is multi-objective optimization based approach. Here, we can also convert a COP into an unconstrained optimization problem along with additional objectives modeled as the constraint violations. This amount of constraint violations must be minimized, and this approach is widely investigated in practice. Okay. We also have selection rule-based techniques like superiority of feasible to manage the constraints by giving more preference to feasible individuals over the infeasible ones during the selection phase. In evolutionary computing, selection is a very major criteria. And in constraint optimization, we have to keep in mind that we should not blindly eliminate all the infeasible solutions. We should take them stochastically, often or infrequently, but also we should give more preference to you know feasible solutions. So that's where selection rules have been modified based on the constraint violation techniques. Sometimes we relax the constraints by an amount of epsilon, and we you know take solutions which violate the constraint up to some degree, multiplicative or additive degree of epsilon, uh, so that we can consider the contribution from infeasible solutions which still hold some valuable information about the optimal functional basin. Okay. Uh, there are also hybridization based approach, repair methods, stochastic ranking, and so on. So, for example, this feasibility criteria is effectively the one which modifies the you know this uh, this selection method in evolutionary algorithms. Anyway, so this is what we are up to. We have so many different solution is always better than the infeasible solution. This is rule number one. Rule number two is among the two feasible solutions, when they are compared in the selection phase, the one with better objective value is preferred. Rule number three is among the two infeasible solutions, the one with a lower degree of constraint violation is preferred. This is a very old method proposed by Professor Kollanmoy Deb long back in 2000. Such feasibility rules can loosely be considered as fitness ranking and preference of lower constraint violation. Then we had Gunnarsson and Xinyao's stochastic ranking, where we use a control parameter PF, which is a hyperparameter predefined by the user, to balance between feasibility and infeasibility. If the constraint violation, ranking of the solution could be done by bubble sort, and if the degree of constraint violation and the objective values are relatively compared, then the choice and preference between two solutions could be drawn. Okay? So what we do is we randomly select a uniformly distributed number u and compare with a predefined pf control parameter. And if u is less than equal to pf or both solutions are feasible, we swap them if f of xj is greater than f of xi. Else, if both solutions are infeasible, we swap them if phi of xj is greater than phi of xi, where phi is some other function, which is the constraint violation. So we are preferring the solution with lower degree of constraint violation, but stochastically, not always. There is a chance factor provided by this uniform distributed random number u and upper limited by this control parameter pf. Similarly, we could have the epsilon constraint approach. The epsilon constraint approach effectively uh, relaxes the limits of the feasibility consideration and then lexicographically orders the solutions. two solutions, we take xi and xj. They can be compared and ranked by their objective values and the degree of constraint violation. If the two solutions are equivalent under the following conditions: if f of xi is less than equal to f of xj, f is the function to be optimized, and both constraint violations phi of xi and phi of xj are less than the limit epsilon or equal the limit epsilon. If phi xi and phi xj are same, then we consider which solution has lesser objective function value. If the objective function value is also same for both the solutions, then we consider which solution has lesser constraint violation. And multi-objective optimization approach generally optimizes the original objective function and also, as separate objectives, minimizes the degree of constraint violation. And this could easily lead to many objective optimization. Many objective means where the number of objectives is more than 3 typically. Uh, but there is a difference between original multi-objective optimization and constrained problems converted into multi-objective optimization problem. The aim of the constraint optimization problem is to find the global optimal solution in the feasible region, but the goal of the multi-objective optimization problem is to obtain the final set of approximated Pareto optimal solutions, maintaining the diversity among these approximated Pareto optimal front members as far as possible. Gradient repair method is one of the uh, widely used methods. The gradient information is derived from the constraint set and can be utilized to systematically repair the infeasible solutions. Gradient information means we have a directional information in the search space, and they are used to, move the infeasible solutions towards the feasible region. Such repair method works effectively if the relationship between decision variables and constraints could be characterized. In fact, gradient-based repair uh, is computationally expensive, and because you have to take the gradient with respect to individual decision variables, and this procedure may require many iterations to reach the feasible region. Top it all, the constraint functions must have to be differentiable, otherwise it may not be possible. Okay? If they are not differentiable, it may not have a meaningful gradient information. So as we saw, the CHTs required to balance a strike, they should balance between minimizing of the objective function and maximizing of the, you know, feasibility of the solutions. This is very, very important. I think that they should strive. Uh, so now, if we go into one of our walks, what we took, very recent walk, it was actually accepted in 2021 but published in 2023 in IEEE Transactions on Cybernetics. It is a mathematical programming approach coupled with covariance matrix adaptation evolution strategy in a simplified manner. Uh, what we do is something like this. This is basically uh, the approach is like this. We know that to solve COPs, balancing between feasible and infeasible solutions in the population is a key role player over different stages of the optimization process. So to keep this balance, we put forth a constant handling technique that we call the V-level penalty function or V-level relaxation or modification of the constraints, which works by transforming the COP into an unconstrained one. Also, to improve the ability of the algorithm in handling several complex constraints, especially nonlinear inequality and equality constraints, we added with it a Broyden-based mutation approach that finds the feasible solution to replace an infeasible solution. And we incorporated these techniques with the matrix adaptation evolution strategy, or MAES, which is a simplified version of CMAES actually. And that led to a new constraint optimization algorithm. So you can see that we are relaxing the boundaries of the constraints. Original boundary is this blue one, and the relaxed boundary is the green one, by some adaptive parameter epsilon v. V is the amount of relaxation given, and this could be different for different constant functions actually. So again, the main role is this, adaptively striking a trade-off between the infeasible and the feasible solutions. So the constraint violation and the V-level penalty approach could be shown in this joint two-stage function. Let me just give you briefly the crux of this mathematics. Uh, we actually presented a new constraint handling technique. As I said, it's called V-level penalty function to transform the COP into an unconstrained one. And unlike most of the previous CHTs that has been integrated with evolutionary algorithms, our technique is utilizing a self-adaptive approach to model the local correlation between the objective function and the constraint violation. Okay. Objective function versus the constraint violation. These two things are very, 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 very important to keep in mind. So we use this correlation information to calculate the fitness value of the solutions. Here, as you can see, objective function decreases as the constant violation increases, and no fixed correlation between the objective function and constant violation usually exists. So we tune the alpha according to local correlation between constant violation and objective function. Alpha is adjusting how much emphasis you are giving between the fitness function value f of x, or the objective function value f of x, and the constraint violation, which is phi of x. Okay. So these alphas are tuned as per the local correlation, and the fitness values of the best solution should be lower than fitness value of the other solution of the population of current or past iterations. If x star is our fitness value for the minimization problem, this first inequality should be obtained, and here from we can get how alpha should look like, and in each iteration we can use alpha k as the maximum between 0 alpha yk alpha y2k up to alpha y capital N k, where capital N is the total number of solutions here. So the V-level penalty function, if we only integrate this penalty function, we see that the performance of the IEEE CEC 2017 function benchmark suit, we took two algorithms. One is, these two are the winning algorithms. Okay, one is Corco and one is VCorp, and we see that in how many cases, this legend indicates in how many cases VCorpo is obtaining best rank. Best rank means lower ranks. In which cases both are obtaining similar ranks or similar performance, and in which cases Corpo is outperforming. So the meaning of this bar is, for the 100-dimensional problem, in 15 cases V Corpo, which is basically the existing algorithm Corpo, plus the V penalty, V level penalty, and two cases Corpo and V Corpo are same, and in 7 cases Corpo is better. So as I said, once again, uh, although epsilon level comparison of the epsilon constant method is good for CHTs on several years, its capability of relaxing the infeasible solutions is more prominent in case the solutions violate a lower number of constraints compared to the situation when several constraints are violated. In the V penalty approach, this is a major modification over the epsilon penalty approach. Uh, Here, the V-level modification is proposed. In this approach, the boundary of all feasible regions are modified, and it is done, as you saw here, by subtracting this V amount from all the constraints in the problem. So if the constraint is, say, gx is less than equal to 0, it is modified as gx minus v less than equal to 0. That means gx would be less than equal to v. That is the relaxation, actually. Okay. And so separate relaxation of the constraints is adopted in this V-level penalty to provide a uniform volume of the relaxed feasible region, which is better than the epsilon level relaxation to explore the optimum solution closer to the boundaries of the feasible regions. As I said, only this V-level penalty, if you add with the winners of the IEEE CEC competition, the winner performances are actually enhancing. There are several such results and benchmark studies in the original paper. Comparison of this V-level penalty with MAGES, which is the matrix adaptive constraint evolution strategy, and the corresponding epsilon penalty plus MAGES. You can see the approaches, how they are differing with each other, how our Broadin based mutation, which is an additional technique to improve the MAES, how that really boosts up the performance. All these things you can see. I will talk about another approach which is very recent, and it's called a reference vector based simplified constant handling technique through a simplified version of CMAES. So, uh, as I said, multi-objective optimization has been very successfully adopted to solve non-convex constant problems. But such works mainly utilize the Pareto dominance based multi objective optimization framework, while the other successful multi objective optimization frameworks do exist, like the hypervolume based ones, like the reference vector based ones, and the decomposition based ones. They have not been utilized adequately in COP solving. Okay. So, what we did in this particular paper, which also appeared in IEEE Transactions on Cybernetics, what we did here is we used the concept of reference vector based multi-objective optimization to design a ranking strategy for the solutions of the COP. So we first transform the COP into a bi-objective optimization problem, and then we solve it by using the covariance matrix adaptation evolution strategy, or CMAES, which is arguably one of the most competitive evolutionary algorithms of current interest. We presented a reference vector-based ranking strategy to calculate the mean and update the covariance matrix in the CMAES. And besides that, the reference vector is explicitly tuned during the optimization process based on the characteristics of the COPs. We also presented in the same work a repair mechanism for the infeasible solutions and a restart strategy to facilitate the population to escape from infeasible regions. All these techniques together create our algorithm. And if you look at this, for each solution I, we actually compute a set of reference vectors, or RVIs, that is determined according to the minimum angle between Ri and 1 minus Ri and the position vector of the solution I. So for each reference vector, the corresponding solutions are ranked according to the minimum value of the projection. And after ranking of these solutions in each such projection, uh, just hold on. Okay. Overall ranking of the solutions is done by supplying more preference to solutions of a reference vector with a lower value of Ri. That means the solution which has lower violation and is surrounded by other feasible solutions, actually, geometrically. That is the actual meaning of it. Reference vector based approaches are very old and common in multi-objective optimization. That technique has here been utilized and, I should say, reinterpreted in context to constraint optimization. And only the feasible solutions are needed to create the actual bi-objective, and it is different from the actual bi-objective optimization problem. Uh, to address this condition, we also presented an adjustment strategy for calculating the RVs to locate the feasible solutions and to rank the non-dominated solutions according to the feasibility rule. So we created an optimum reference vector for that. Then there is some how we are actually using these reference vectors and the angular distances from other vectors to minimize the original reference vector for the feasible pairs, etc. That has been described. The performance was benchmarked for the IEEE CEC 2017 and our own real parameter benchmark that I talked just at the beginning. And we could see commendable performance results for different dimensionalities where this RCMAESG is actually our algorithm. Okay, in the previous paper, we also used a specific method of repairing. I talked about this V constant paper. So in the V constant paper, I talked about the V penalty only, but we also came up with a specific repair mechanism that is called Broyden-based mutation repair operator. Uh, this repair operator actually finds a feasible point closer to the infeasible solutions and drags the infeasible solution towards that closest feasible point, as you can see. So this dragging is done through these such steps, which you can see here. Uh, and it requires only one function evaluation in each iteration except for the first iteration. So the gradient-based repair mechanism is actually taking some sort of approximation or inversion of the uh, of this matrix J of xk, which is basically the Jacobian matrix of the function set. And Jacobian matrix contains the first order partial derivative information. In the Broyden-based, so this is gradient-based repair. In the Broyden-based repair, actually, we do not have to calculate the entire Jacobian matrix, but we can approximate it with this, iteratively refining matrix B inverse. And there is mathematical principles of designing this. The actual geometric interpretation is we drag the infeasible solutions to their nearest feasible solutions through steps and over iterations. So if we compare the Broyden-based and gradient-based repair methods, we see that the Broyden-based operator is quite outperforming the other one over several functions from the IEEE CEC 2017 problem set of COPs. And finally, we combined it with the Levenberg-Marquardt optimization approach, which is a second-order optimization approach, uh, and robustifies the Broyden's update method, being not so sensitive to the initial seed of solutions. Even if the initial seed is very far away from the boundary of the feasible region, then the LM with Broyden's update method can tackle that. So the full algorithm has been shown here. In our case, covariance matrix adaptation evolution strategy is a mathematically inspired, derivative-free, distribution-based evolutionary method for solving non-convex continuous optimization problems. That particular algorithm was used as the code optimizer. I'm not going through these steps because they are mathematically quite troublesome. But what I try to tell you is that this SCMAES or DE, differential evolution, SCMAES is specifically suited in this case because as an optimizer for the non-convex nature of the problems and their ill-conditioned trajectories, CMAES appears to be a very, very interesting algorithm. Okay. So that's why I shifted from my usual comfort zone, which is differential evolution, and tried CMAES, tried actually the simplified CMAES. Uh, and the core difference is it replaces the adaptation of the covariance matrix C with the adaptation of the square root of the covariance matrix, which is M. So M into M, M transpose M is actually C. And the simplified variant of CMAES is added with our this reference vector based approach. Uh, the it actually the square root of the covariance matrix is directly approximated to avoid the use of eigenvector decomposition, which is computationally quite expensive and probably a little bit unstable too. So the MAES is more stable and less computationally expensive than CMAES. So MAES can still remain a level of performance almost similar to CMAES. Moreover, the matrix adaptation equation, order of n square used in MAES, can easily be removed by iterative sampling equation to reduce the space complexity and time complexity of the MAES. There are, analysis of such reduction of time complexity and space complexity in the original paper, but this is a very good candidate algorithm for solving multi-objective optimization problems or scenarios. So finally, let me just try to conclude. These are mathematical techniques and time is very limited. So first of all, as I said, in constrained optimization problems, several topics needs to be revisited. For example, the design of constant handling techniques for dynamic and multi-objective problems. Dynamic problem means where the fitness landscape can change over time. You are tracking with the optima of the problem. You are actually trying to locate a time shifted optima. If you have very expensive sort of function, you may want to approximate the fitness using surrogate methods. You may want to use hyperheuristics, mixture of several small heuristics to optimize the algorithms. You may want to study the functional fitness landscape of the optimization problem in presence of constraints. You may want to look into the theoretical foundations and convergence behaviors of such optimization frameworks in current use. Uh, Improvements of CMAEs and similar algorithms could be attained through meta-modeling. This is a term used to mean that the constraint boundary surrogates can be used for prediction of feasibility of mutations and for repair of infeasible solutions. So constraint boundary surrogate means if the constraint function doesn't have a closed form, we can actually approximate its boundary by using a neural network or some other neural architecture actually. This meta modeling can help us to solve complicated, expensive constraint optimization problems. And then usage of machine learning techniques like a rule-based reinforcement learning can guide us or guide the population of an EA towards the feasible optimal design of attraction. Finally, mimetic algorithms, which actually try to mix up a local search method with global search heuristic, they are becoming extremely popular in the literature, even surpassing other hybrid approaches. So, developing a new local search strategies that are specifically designed for constrained search spaces, depending on your specific nature of your problem, is becoming a highly relevant research topic. So the field is quite vibrating, and there are new challenges emerging every now and then, especially in relation to neural architecture search and other problems. You could take a look into this, but try to also understand the mathematical underpinnings of the field. So with this, I would conclude and thank you very much for your kind patience. If there are questions, I can take those now.
Hello, sir.
Yeah, yeah.
Yes, participants, I request you to put your questions in the chat box. Please do write your questions. Swagatam, sir. Your video.
Okay.
Sir, you can look at the chat box. Sir.
Ashwin has asked a very good question. In the era of AI, ML, and generative AI, where does this optimization techniques stand? See, evolutionary computing or meta-heuristic optimization for domain-specific hard optimization problems, their role is still contextual, I would say. Hard optimization means such thousands of variables, lots of constraints, and it's very difficult. You don't know the optima. For example, in drug design, in stable molecule design, we may have a 13 atom molecule, and for each atom, we know three coordinates of each atom. These coordinates needs to be optimized so that the entire molecule is thermally or I mean based on energy function, it is stable and at a minimum energy configuration. Such problems may be Lennard-Jones molecular cluster problem. These are hard optimization problems, and there is no way to solve them mathematically in a guaranteed way. However, neural networks, huge, large-scale neural networks, could still be, you know, trained to learn from their previous experiences about the functional landscapes, and then they can be used to solve such problems. And you might be aware of such a problem, such a breakthrough in 2024, which came through this AlphaFold from Google DeepMind. AlphaFold actually solved a typical very tough optimization problem related to protein structure prediction. So protein structure prediction, initially several people tried evolutionary algorithms to solve it, but AlphaFold, using its huge, big, deep neural architectures and reusage of past experiences, solved it in a completely different manner. That earned the Nobel Prize of Chemistry in 2024. Actually, AlphaFold came, I think, in 2023 probably. And the Google DeepMind CEO and his collaborators got the Nobel Prize because of that breakthrough. Compared to such breakthrough, uh, the role of just publishing a new evolutionary algorithm on very simple problems is very limited and not contextual. That doesn't add any value to the real world problem solving area. So if you can really solve a very tough problem like this molecular distance geometry, as I said, or drug design, for which there are specific benchmark sites which list the best solution obtained so far and so on, then it makes sense. So that's why I was mostly involved in combining real world optimization problems instead of toy benchmark functions. Now there is a very bad trend in this area, which is you take any natural nature or natural phenomena or creature, then you formulate some very easy equations, which are actually the repackaging of old things from PSO, DE, etc. And then you run it on very simple toy functions. Such research has become completely obsolete, incontextual in face of AI, ML, and generative AI. This is the answer to Ashwin, actually. Thank you. Any other question? See, there are no more questions.
Yeah.
We can close it,
Yeah.
right?
Sir. There are no more questions. Thank you, sir, for giving two very important lectures in this particular faculty development program on advanced optimization technique using MATLAB. And you have been associated with us from long back,
Long time,
a
long time.
long time, and over a series of uh, times we have conducted this particular FDP, and it has been widely participated from all across the researchers from various institute and faculty members of various institute of our country. So thank you for your consistent support, sir.
Thank you very much. Good time.